Welcome to this overview of operating systems, where we'll unpack the core ideas that make modern computers work. Over the next slides, I'll guide you through how an OS manages resources, schedules work, handles memory and storage, and provides safety and isolation, using clear visuals to connect each concept so you can see the big picture and how the pieces fit together. This page frames the OS as a resource manager, like a director on a production line, who schedules tasks and allocates limited tools. The illustrations show managers assigning work, and the OS mediating access to CPU, memory, and I/O, ensuring fair access, resolving conflicts, and protecting resources so multiple applications can run smoothly without stepping on each other. Here we compare processes and threads. A process has an isolated address space for code, data, heap, and stack, while threads are lightweight paths of execution that share a process's memory. The diagram highlights how the scheduler saves and restores context to create the illusion of simultaneous execution, letting many threads make progress on a single CPU core through fast switching. This slide explains how the OS hides storage and memory complexity with an abstraction layer. Virtual views, paging, caching, and persistent files are presented as uniform pages mapped to physical frames or disk blocks, supporting features like demand loading, copy on write, and transparent sharing. So, applications see a simple memory model, while the OS optimizes real hardware use. A core OS idea is separating mechanism from policy. Mechanism implements basic primitives like context switching and memory allocation, while policy decides what to do, such as which scheduling strategy or security rules to apply. This separation lets administrators tune behavior priority schemes, access controls, or memory strategies without rewriting kernel code, giving flexibility and practical configurability. This slide shows how workload analysis guides OS architecture for different goals. Desktop interactivity focuses on responsiveness and low latency, server throughput emphasizes efficient batching and resource utilization, and real-time systems require predictability and strict timing. The visual ties data structures, caching layers, and scheduling algorithms to each goal and stresses, preserving correctness under edge conditions. Monolithic kernels use a unified kernel image that integrates device drivers, file systems, and network stacks into one address space for direct function calls and strong optimizations. That design offers performance, advantages, and easier global tuning, but it also concentrates risk. A single buggy component can crash the whole system, and the large memory footprint and maintenance complexity are important trade-offs. The microkernel architecture takes a minimalist approach by pushing services like device drivers and file systems into user mode servers, leaving only IPC, basic scheduling, and hardware control in privileged code. This yields a small, verifiable core and better fault isolation, while trading off increased context switch overhead and more complex inter-process communication for modularity and reliability. Process management centers on the process control block, which stores, registers, memory maps, and open file handles to represent each process. The state transition diagram shows how processes move between new, ready, running, waiting, and terminated, driven by scheduler decisions that use priorities, time slices, and I/O events to determine which process runs next and why. Concurrency requires kernel coordination primitives so shared resources stay consistent. The slide outlines common solutions: atomic instructions, mutexes, condition variables, shared memory segments, and message queues, showing how the kernel helps threads avoid races and achieve deterministic, ordered updates across parallel activities, which is crucial for correctness in multi-threaded programs. Virtualization introduces a hypervisor layer that presents each guest with virtual CPUs, memory, and devices, while multiplexing the real hardware beneath. The illustration highlights benefits like higher utilization, seamless migration of instances, stronger isolation for security, and legacy support for running older systems, all made possible by translating and managing resources at the hypervisor level. The final slide contrasts hypervisor architectures. Bare metal. Type 1. Hypervisors run directly on hardware and control resources via privileged domains or built-in drivers for maximum performance and control, while hosted Type 2 hypervisors run on a standard OS and rely on it for device support and management, trading some performance for ease of deployment and broader hardware compatibility.